All right, so we're going to talk about distance traveled. Remember, first semester we were talking about rates, speeds, velocity, that kind of thing. This is distance traveled, something called the rectangular approximation method, which fortunately for West Valley High School students is abbreviated RAM, so it feels a little personal there. Potentially get to talking about the volume of a sphere and examples such as cardiac output. And why are we doing this? Because learning about estimating with finite sums sets a foundation for understanding integral calculus. And there's kind of the first hint of a different kind of vocabulary for this semester. And so my initial question here that I need people to think about and possibly will be helpful if they respond audibly, okay? If we have a train that is traveling at a constant speed of 75 miles per hour, how far will it travel between its first and fourth hour of travel? I'll let you do a little calculation there. So I've got a couple of answers here. Okay, I've got a 225 and a 300. I've got another 300 coming along here. I got another 225 coming along. Okay, and more 225s. Okay, I got a 300 change to a 225. We got another 300 popping in. So, is anybody willing to explain how they got what they got? Somebody willing to explain their 225 answer?
I can.
Okay.
So I took 75 miles per hour and multiplied it by the first hour to get 75 miles. And then I took that same 75 miles per hour and multiplied it by 4 hours to get 300 miles. And then I just subtracted the difference between the two.
Okay. So in the first hour it traveled 75. In 4 hours it was 300. So between hour 1 and hour 4 was the 300 minus the 75 of the 225.
Yeah.
Okay. All right. That makes sense to me. Does anybody want to come back from the 300 and say, hey, wait a minute, you forgot something? I'm watching the chat, by the way. You see me just standing here. So the 300 I agree with in terms of the first 4 hours. So if it traveled 75 miles an hour for 4 hours, it definitely would travel 300 miles. But if I'm asking for just how far it traveled between the first and the fourth, then I think I have to leave that first hour out, and I agree with the 225 on that. Okay. But how could this, or why would we even bother wanting to represent this graphically? Well, if I did represent it graphically, usually I've got time involved here, and so maybe putting my 4 hours on the x-axis, time usually goes on the x-axis. Okay. And on the y-axis, if I put my velocity, or my speed, let's just call it speed because there's probably not 300 miles of perfectly straight track anywhere. We'll do our speed in miles per hour, and if we said this was the 75, then here is the graph of the speed. And we went from hour 1 to hour 4. So now my question is, where is 225 on that graph? After 3, okay, so at the 3, visually, where is the 225? On the 75 line, okay. Of the 4 on the blue line, up here. I'm still not exact. I see 75s there and 3s and 4s. I'm not seeing a 225 just yet. The z-axis. We want to come out of the screen and go 3 dimensions. Okay. That would be exciting, but probably not where we need to go yet. Okay. Certainly 3 dimensions is fun to think about, but I think I agree with Jacob on that one. I don't think that we need to go there. So how did we get to 225 again? Or the people that got to 300, how did we get that? Imagine the y-axis to be distance, so you added more a linear equation than this. Okay. Except that I know that people did a calculation to come up with those numbers. So what kind of calculations were you doing? 75 times 3 is 225. Okay, I had someone talk about distance between 1 and 4. So the distance between 1 and 4, here, this distance is certainly 3 hours there, and the 75 up here, okay, and here multiplication, certainly when we learned multiplication way back in the very beginning, it was drawn as like rectangles, right? And so this rectangle, if we look at it, is 3 hours wide and how tall? $75 miles tall, 75 miles per hour tall. I got to write the 5 there, or it won't make any sense. It is 3 hours wide and 75 miles per hour tall. Now, if I tried in the 3rd grade when you were introduced to multiplication to talk to you with these units on there, it probably wouldn't have gone over real well. Okay. But the 225, we know from the multiplication, that should be the area of this rectangle, right? So the 75 times 3, that's definitely 225. And when we do the units of miles per hour times multiplied by units of hours, well, I got hours in the numerator, hours in the denominator. Those should cancel, and it leaves me with an area of 225 miles. Okay. So that's where the 225 is in this picture. If we have the constant velocity up here of 75 miles per hour, we blocked off a 3-hour unit of time on the bottom, and if we then used multiplication and kept track of the units, then it actually tells us that this area in here represents the 225 miles that the train traveled in that time period. It's important that that makes sense to us. Are we feeling okay about that? In the chat would be great, because that's what I can see from here. Okay. So, this was pretty easy, right? What would make it more complicated? Another axis, a curve. So if this was about a car instead of a train, I believe that I might be able to find a place where a train could maintain a constant 75 miles per hour for 4 hours, maybe. But I don't think I could pull that off in a car. Right? In a car, my speed is always fluctuating. I've got to go faster in some places, I have to slow down. In other places, I've got all of this changing going on in there. You could, it just might not be legal. 75 not too bad. You get into eastern Montana there, maybe. I don't think 75, going uphill, your car may not be able to hold that. That was certainly my car in college, the 1984 Subaru wagon. Okay. Did not get along with hills at all. All right, so what would this look like? We'll keep the 4 hours, it doesn't really matter. Speed in miles per hour. And who knows, maybe we do have a 75 up here, but as I'm driving in my car, maybe my speed looks something, well, probably not that one back there. I don't have that kind of acceleration. All right. So, maybe my speed over that time looks something like that. Or maybe very different than that, but this is certainly a possibility. And if I'm interested in how far I traveled between hour 1 and hour 4, following the pattern from before, what I would need to know is what is the area of that? And what's the problem with finding the area of that? Hard. Okay? It's a weird shape. Yes, we won't let it know that you're called it weird. Okay? Don't want to offend any of our shapes. Okay. But it certainly is a shape that we don't have a formula for. This is not one of our standard geometric kind of shapes that we have formulas for, like all of our polygons and circles and those kinds of things. Okay. So, and it has this unusual shape because that speed is always changing. Our output numbers are not always the same. All of these insights are good insights that it wouldn't hurt for everybody to see them. Okay? So, does that mean that it's impossible to figure out how far this car traveled between hour 1 and hour 4? I mean, certainly the odometer on the car, if you were paying attention to it, will tell you exactly how far you went in that amount of time. Okay? But this is the heart of what we're trying to figure out how to do in the second semester. Okay? So our second semester is going to be problems like this. And can we find that area exactly? Or can we at least come up with really, really good approximations of what that area is? Okay. That's our goal for a little while here, and we're going to take different approaches to that. Obviously, if we don't have an equation for this, we would at least need to have some kind of data points to work from, that maybe as somebody was driving every 5 minutes or every 10 minutes, they looked down to see how fast they were going at that instant, and they kept track of that, then maybe that might help things out a little bit. Okay? We have to think about that a little bit as to our approach, but that is the connection. This is our visual of what's going on here. Is what was very easy here because the speed was constant, and we were able to come up with that area because it made a geometric shape that we know a formula for. In calculus, we don't let things get that straight all the time. And we deal with things maybe the way that they really are, and we're still trying to find an area here, okay? And it won't always, the area is a good picture for us to help understand what it is that we're trying to accomplish. So, that's how we're getting started here. Okay. The rectangular approximation method. Okay. I've got a few of them up here. What the rectangular approximation method does is it says, well, what if we're trying to find this area under that's trapped here. So this looks very much like a parabola that's probably going along there. And if we were trying to go from 0 to 3, say, then what we're trying to find is this area under that shape. Now it's much less erratic shape. It looks kind of like a triangle maybe. In fact, it wouldn't necessarily be a horrible starting point to say, well, let me see what the area of this triangle would be. If I did the area of that triangle, it overshoots by this amount. There's definitely too much stuff there. I would get an answer that was too big if I tried to just do it with a triangle. The rectangular approximation method says, well, let me make some rectangles, okay? And I have choices when I make the rectangles. So first of all, I have a choice of how many rectangles should I make, okay? If I only make one rectangle, then my rectangle would be 3 units long, and I would have to decide how tall I want to make it. Any thoughts? If I make that 3 units long, how tall should I make that rectangle to try to get a guess at what that area trapped under that curve should be? 3 tall? I don't really know where 3 is, I guess, off the top of my head here. I don't know what this curve is exactly, but somewhere along here, I could definitely say it doesn't make any sense to make it this tall. Right? It doesn't make sense to make it that tall because I know it's definitely trapped under that point. So if I'm looking at things, anything up here would just be ridiculous in terms of trying to get an estimate of what that area is. Okay? This is the first thing that even kind of makes sense, right? In fact, this is very closely related to making the triangle, because if I calculated the area of that rectangle and just cut it in half, I'd have the area of the triangle. Okay, so knowing what the area is under that green line is the first thing that makes sense. This down here doesn't make a lot of sense, but it makes more sense than this. I certainly wouldn't want to say that it's a negative height on that rectangle, whatever in the world that means, right? So definitely somewhere between here and here are the only ones that make any logical sense at all. This would give me approximation of 0. I know it's definitely more than that, and I know it's definitely less than whatever this would be. And I'm pretty confident it's less than whatever this would be, but there's maybe some magic point in here. Hard to figure out exactly what that magic point would be. So in this case, they decided to make 6 rectangles. Okay? There is one here at the very beginning. It just has no height at all. So this method over here is commonly in this book anyway, referred to as the LRAM method. Okay? Because what it does is it says, okay, pick the number of rectangles that you're going to make and make that many, break up the x-axis into that many equal-sized spaces. Okay? And then we're going to decide on a height for every one of the rectangles that has each of those bases. So we've made these 6 equal-size pieces along the x-axis here. And for each one of those, we have to pick a height. The LRAM method, the L in the LRAM method says that go to the left-hand side of whatever little interval you're working on. Okay? So if we were looking at this particular one, this is called a subinterval. If we were looking at this subinterval, the LRAM method says go to the left-hand side of that and figure out where that left-hand side, okay, the x value on that left-hand side, what is its output? Okay. And use that as the height of the rectangle. So if we will approximate what we think this equation is here in a little bit and kind of work through what that looks like. But what it does then is every subinterval, you look at the left-hand side, you plug the x-coordinate from the left-hand side into the function to figure out how tall it was, how tall you're going to make the rectangle. And you're going to make it based on what the output of that left-hand endpoint is. Okay. Is that making sense so far? Okay. I've got one yes. It needs to make sense to a lot more people. Okay. Okay. So yes, but why do we use the left-hand side? So using the left-hand side is one choice that you could make. Okay. And if we looked at the thing overall as a picture, when I made just the one rectangle out of it, this red line down here, that would have been choosing the left-hand side to decide how tall it was going to be. Okay. And we have lots of different ways that we could choose this. So in this last one over here, okay, if I look at the one on this side, and I have my little subintervals in here, and I'll grab this one in here. If I was looking at this particular subinterval, this one says, try the right-hand side. Okay, so if your x's, and we could label these, we know that this is a half as an x. This is 1. We had a 1.5 there. This one is at 2. There's a 2.5, and this one's at 3. So this method, which is the RAM, or for everybody that had Spanish, the RAM. Okay. It's so much more satisfying when people chuckle out loud in class when I do that. All right. So, if we choose the point on the right-hand side to plug in and see how tall it is, then that's what's happening here, and it's saying find that area. You know that it's a half a unit wide. You've plugged the 2 in to figure out how tall it is at that point, and so you can do length times width to approximate what that one little area is there. So I'm seeing another question in here. What if it's the farthest left interval? So on this farthest left interval over here, we did, in this example, it had an output of 0, so that was a rectangle that is half a unit wide and 0 units tall, so it contributes 0 to the total here. Okay. All right, so the question is, if the rectangles are below the line, you use the left, and if they're above the line, you use the right. That has more to do with the shape of this particular function. It's not always exactly that way, okay? Because of the way this function is shaped, okay? And all of these are, again, trying to find out what the exact area is, right? So I'm going to draw it in this middle one here for a second. What we're shooting for is we want to know exactly what this area is, okay? And on the left-hand side here with the LRAM, it's saying one way to approximate exactly what that is to break it up into rectangles and approximate the area of the rectangles by using a height that comes from the x value on the left side of each one of those rectangles. Okay. On the far right over here in our RAM, it's saying, no, approximate it by what's on the right. And looking at these shapes right now, we can see that the LRAM is going to give us a number that is too small, right? Because the LRAM is going to add up the areas of these rectangles, and it's going to miss all of this stuff. Okay. So it's going to give us the total of what's in red. It's going to miss everything that's in blue. The RAM is going to give us everything here in green, and the problem with that is that answer is going to be too big. Okay, it's going to be too big because it's going to overshoot by this amount. We're going to have all this extra up here that it adds into the total. All right, so there was extra stuff added on in the RAM, in this case because of the shape of the graph. Okay, and on the left-hand side, we've got not enough. Okay, so one thing, if you've got one answer that you know is too small and one that you know is too big, then a lot of people would say, well, let's just average them and shoot down the middle somewhere. Okay, and that certainly is a valid thing. You're going to get a closer answer, especially with the graph shaped this way. You're going to get a much closer answer if you average those two answers together. Okay. But this one here in the middle, one in the middle says, okay, keep doing what we were doing. Break it into your little rectangle bases here. So we're going to break it into 6 parts again, 0.5 and 1, 1.5 and 2 and 2.5 I know those are completely illegible. I can barely see them from where I am. Okay? And this says, well, let's try something different. If going on the left was too small and going on the right was too big for this shape, what if I picked a value that was right in the middle? So let me pick 0.25 and 1.75 and 1.25, right, and 0.25, 0.75, 1.25, 1.75 in there, and then I've got a 2.25 and a 2.75. And what if I plugged those x values in to see what their y values were, which is what these points are? Right? So this is the point here. This is the point 2.25 comma f of 2.25, whatever that function happens to be. And it says use that as the height. Use the one in the middle. If the left is too small and the right is too big, then let's go right down the middle with something. And this is, they're going to call this one MRAM. Okay. And really, with these approximation methods, these rectangular approximation methods, that's just 3 of them. There are an infinite number of these, because you could say things like, okay, make your little bases, split up into as many rectangles as you want, and then maybe go 20% along the way and use that as your choice of how tall you're going to make it. Okay? Or there are methods where it's not consistently using the one on the left or the one on the right or the one in the middle. It might say always use whatever value in there gives you the biggest possible number. Okay? So these can be defined in a lot of different ways. Now this one, we see this would have a little bit of area there and a little bit here. And the advantage maybe of this one is it counts some stuff that it shouldn't, but it misses some stuff that it should, and maybe that in some way balances out a little bit, right? So it's counting this, which isn't actually part of the area. But it's not counting these little blue pieces in here that it should. And maybe in some way that there's a balance between those two things. Okay? All right, so the question is, what number are we plugging into the equation, and what does that number give us? This is all about finding areas of rectangles. Okay, if you want to find the area of a rectangle, you need a base and a height. Right? The base is determined when they tell you we want this in the first 3 hours, to use our example from before. Okay? And then we decide, well, how many rectangles do I want to make? In this case, they decided to make 6 rectangles. It's kind of an arbitrary decision. Okay? And so if we make 6 equal-sized rectangles, then we know the base of all of our rectangles will be exactly 0.5. Because we're going from 0 to 3, that's 3 wide, divided by 6 into 6 rectangles. Each one of those is a half a unit wide. The other number then that we need for the areas of our rectangles is how tall are they. Okay? And it only makes sense if we're going to do an area of a rectangle that we've got this curve that goes through there that we're trying to approximate, and so we shouldn't make it any smaller than the values of the curve on that interval. Okay. So I'm going to erase some stuff here. If I was focusing on this interval, okay, from that's 1 to 1.5, okay, it would not make any sense for me to make that rectangle this tall. Okay, because this curve, the part of the curve going through here, Okay? If I'm trying to approximate the area that's under this, that would be a ridiculous approximation. Okay? The only approximations that possibly make sense are the ones where that maybe are this tall or maybe only this tall. Okay? It doesn't make sense to go any lower than that, and it doesn't make sense to go any higher than the other one. Okay? Because all of the outputs of the function are trapped between these two y values. So if I know that the area under there is somewhere between those two, so it wouldn't make sense to choose any other heights than some height that's between those. And so what the rectangular approximation method does is the LRAM says approximate the height by using the 1, because the 1 is on the left-hand side of this. Okay? So the LRAM would say choose the height by using a 1, the left-hand side of the interval, and plug that 1 into the function to use that output as the height of the rectangle. The RRAM would say use the 1.5, use the point that's on the right-hand side, plug that into the function to come up with a y value and use that y value as the height of the rectangle. The MRAM would say find a point that's exactly halfway between 1 and 1.5. That's my 1.25. Plug that in there. Plug that into the function to come up with what the height is going to be and use that as your approximation. Okay. So the number that we're plugging in is some number, in this example, between 1 and 1.5. It could be 1, it could be 1.5, it could be any other number in between those, because we know that when we put those numbers into the function, we will get an output that is, somewhere in the right range for approximating how tall we should make the rectangle. But never ever forget that it is about finding areas of rectangles, and you can find areas of rectangles. Okay? We're not going to get to a new assignment here just yet. I think we have the ability to start out pretty deliberately in this. Yes, we would need some kind of information like the equation for this, and this maybe looks like f of x is a half x squared or something like that. Okay? And so if we know what it is, then we can plug the number into that function and come up with a height. If we don't have a function, we would at least have to have some data table that tells us what the outputs were for particular inputs. So our y-axis isn't even marked here, so we have no idea what this function is, other than we're pretty confident that it looks quadratic. So, does the second semester incorporate derivatives? Absolutely. In a couple of different ways. One is that eventually derivatives are going to be a way of checking our answers this semester. Okay? And then there are also some techniques for coming up with the answers that we're going to do that require you to remember some of those derivatives along the way. So that is about it for our time today. We didn't get a long way on here.